1 meter squared area makes an angle of 60 degrees with the uniform magnetic field. The magnetic flux through this area is the same as the flux through second area that is perpendicular to the field if the second area is 0.5 meters squared. Suppose this page is perpendicular to a uniform magnetic field and the magnetic flux through is 5 Web. If the page is 10-30 degrees around an edge, the flux through it will be B, 4,3 Web. Number 30. Therefore, the normal to a certain area makes an angle of 60 degrees with a uniform magnetic field. The magnetic flux through this area is the same as flux through a second area that is perpendicular to the field if the second area is C, 0.5. Suppose this page is perpendicular to uniform magnetic flux 5 Web and then 30 degrees around an edge. Flux will be B, 43, 4,3 cover. 1973 man, 1974. Oh, 1979 minus 2023. Okay, Papa now there 43. Therefore, a 2 Tesla uniform magnetic field makes an angle of 30 degrees with the z-axis. The magnetic flux through a 3 meter squared portion of the xy plane is C, which is 52. I'm sure someone is 52. I don't know who, but I'm sure Matu. And then a uniform magnetic makes an angle of 30 degrees with respect to the z-axis, and therefore if the magnetic flux through a 1 meter squared portion of the xy plane is 5 WB, then the magnetic flux through the 2B is, I was going to say 10. Okay, it's 10. They doubled it. 1 Web is equal to 1 Tesla times meter squared. Or you could just in 1 volt times second. The units of motional EMF are E Tesla meter squared divided by second. Faraday's law states that the rate of change of the magnetic flux says that an induced EMF is proportional to the rate of change of the magnetic flux. Rate of change of the magnetic flux. The EMF that appears in Faraday's law is B, is around the boundary of the surface used to compute the magnetic flux. If the magnetic flux through a certain region is changing with time, an EMF must exist around the boundary. D is the answer. A square loop of wire lies in the plane of the page. A decreasing magnetic field is directed into the page. The induced current in the loop is V. Clockwise. As an externally generated magnetic field through a certain conducting loop increases in magnetic magnitude, the field produced at points inside the loop by the current induced in the loop must be directed opposite to the applied force. At any instant of time, the total magnetic flux through a stationary conducting loop is less in magnitude than the flux associated with an externally applied field. This might occur because applied field is normal to the loop, increasing in magnitude. A long straight wire is in the plane of a rectangular conducting loop. The conducting wire carries a constant current I, as shown. While the wire is being moved towards the rectangle, the current is in the rectangle is counterclockwise. Strong. And then this one is also counterclockwise. Increasing current in the direction shown. The current in the rectangle is okay. We are moving it towards the rectangle. It's gonna be currently being a rectangle. But then if we are shutting off the current, in the rectangle is it will move clockwise. The rectangular loop of wire is placed midway between two long straight parallel conductors as shown. The conductors carry currents I1 and I2 as indicated. If I1 is increasing and I2 is constant, the induced current in the loop is C, which is counterclockwise. So it goes from I2 to I1. And then the cycle depends. The cycle goes back and back.